So now that we've gained some experience with rudimentary Newton's second law problems, okay, or kind of entry-level Newton's second law problems, now we want to start looking at problems that work on the same principle, but kind of have more parts, okay? Putting a little more meat on the bones here, okay, for these types of problems. They still come down to the same two things. Regardless of how complex a Newton's second law problem gets, no matter how many parts there are to it, it always comes down to sum of all forces and m times a. Okay? Now, I showed you this one yesterday, and then I said, I'm going to be nice, I'm not going to do that one today. But we're going to do it today, because today's a different day, and I'm less nice today. Okay? But you're also ready for it. So, just so you know. All right? Because it's really not as scary as it might look upon first glance. Okay? So, what I want you to do is kind of visualize. If I had this situation in front of me, which incidentally we do, okay? And I pulled on just the front string, what would happen? It'll move. Will both boxes move?
Yeah.
Why? Because they're attached. Exactly. Will they move in the same way?
Yeah.
Okay, so there's some dissension here on this one. Okay. Think of it this way. When a semi-truck accelerates, do the truck and the trailer accelerate at the same rate? They better. If they don't, they're coming apart. Okay? And the last time I checked, that doesn't happen most of the time. Okay? A truck and a trailer is exactly what we have here. Okay? We have two objects that are in what we call a system. Okay? A system is a series of interconnected parts. Okay? These are two interconnected parts. If I pull on the string, I pull directly on the 10 kilogram mass, I pull indirectly on the 20 kilogram mass. But because they're connected, they have to accelerate at the same rate. If they don't, the 20 kilogram mass either falls behind, which could only happen if the rope broke, or catches the front one. And the last time I checked, trailers don't pass the trucks towing them, except for jackknifing on icy roads, but that's a Newton's first law situation. It's not a Newton's second law situation. Okay? So, what we have then is that if I pull on this rope, both parts accelerate at the same rate. Okay? They have to. Now, is that important for me to know? It is. Because now I know the acceleration of the system, all of the mass, and the acceleration of each individual mass. I know they're the same. Okay? So what I can essentially do is I can look at this problem from two different points of view. I can look at it as two separate masses with the same acceleration, or I can simplify it. Because what's really going on is I'm pulling 30 kilograms worth of mass. Since it's all moving together, it's all really one big object. Okay? Now, there may be a situation where I have to separate them and deal with them separately, but in the real world, I'm pulling 30 kilograms worth of mass. I'm pulling all of it at the same time.
That's a bad diagram. I don't know if anybody can just put 60 kilograms
With a little string? Yeah. I mean, we are looking at almost 135 pounds there. Yeah, with a dinky little string, but yeah. It's a lot, but it's a friction, maybe it's a frictionless surface. It does say that, right? On a level surface, it doesn't say anything about friction. So on a frictionless surface, you'd probably be able to do this. Yeah. Where you get a frictionless surface from, I don't know. Okay? All right. So two blocks of identical material are connected by a light rope on a level surface. An applied force of 55 newtons to the right causes the blocks to accelerate. Okay, so this force right here is 55 newtons. Okay, so really what I'm doing here is kind of drawing my free body diagram. Okay, while in motion, oh no, there's friction. The force of friction on the system is 44.1 newtons. Calculate the acceleration of the blocks. Okay, so this system is all going together. Agreed? Right? When I pull on that first string, all 30 kilograms accelerates together. Okay, so then I can do this, what I was saying I would do. Simplify this system to one big mass, because it's all got to go together. So this is 55 newtons, and this is 44.1 newtons. Okay, gravity's irrelevant here because it's on a table and it's canceled out by the normal force. Okay, so those are the only two forces that matter. What do I do next? Find F net. Yeah. How do I do that? Find the vector sum of the two forces. So F net's going to be my applied force, that's the 55, plus the force of friction, my 44.1. All right, so F net's going to be 55 minus 44.1, which should be 10.9 newtons forwards. Okay, question doesn't want net force, question wants acceleration. What do I do next? Right, F net equals mass times A. All right, I want the acceleration. Divide both sides by m. So I've got 10.9 divided by 30 kilograms gives me my acceleration. Okay, so the acceleration of the blocks of the whole system, of either block, okay, is 0.36 meters per second squared. And it's just say forward here. I don't see right or left on here, so forward. Did I do anything different with that from an elevator question? No, I didn't. Okay? Other than I had to look at something that was two objects and say, well, they're connected, so they have to move together. That was really the only thing that was different. Okay? From all the other problems we've done, that was all that was different. Was I had to recognize that in a system, the acceleration of all the parts is the same. Okay? And that they would move as one. Okay? Questions on how that one worked? Right? We didn't do any more work on that question than any of the other ones we've done. Okay? Now, I'm not saying that's where it stops. It's not. Okay? A question could now say, all right, what's the tension in this rope? Okay? If that's the case, now I break the system up into pieces. I know the acceleration of the 20 kilogram block. I just calculated it. Okay? Every part of that system is accelerating at 0.36 meters per second squared forward. Could I calculate the net force on just that last block? I could. Okay? And as long as I knew the force of friction acting on that block, I'd be able to calculate the rest of it. Okay, I want you guys to try question number 1 here. It's very much like the one we just did. Okay, it's 2 buckets of nails being pulled upwards. Okay, I'll give you a few minutes on that one. First thing, draw the free body diagram. Okay, draw the free body diagram, and you gotta. This one you gotta see through it. But maybe that's not good. But you do. You have to see through it. Okay. Okay, so I've got 2 buckets of nails, and they're connected to each other, like this. Okay, and there's a rope pulling on the first one. Okay, so each bucket has a mass of 5 kilograms. Okay, the tension in the rope connecting the buckets is 60 newtons. All right, so that means that the force right here is 60 newtons. Okay, calculate the acceleration of the buckets. All right, what do I have to recognize about these buckets? What do they have that's going to be the same? Their acceleration. So if I can calculate the acceleration of either one of them, do I know the acceleration of both of them? Okay, that's my first step, is being able to recognize that this is a system and all parts have the same rate of acceleration. So, what I'm going to do, I'm going to ignore the top bucket. Because I don't know how much force is being used on the top bucket. I could assume it's 120 newtons, but I'm not going to. I don't have to. It's dangerous to make assumptions. Okay? We could be wrong, so we don't want to do that. What we do know for sure is there's 60 newtons of force pulling up on the bottom bucket. What's pulling down on the bottom bucket? Gravity. Okay, so I got gravity pulling down on the bottom bucket. I can calculate gravity by going m times g, which is going to be 49.05 newtons. 5 times 9.81. All right, what can I calculate now? I can calculate F net. Okay, and it also equals the vector sum of all forces. So we're going to say applied force or tension plus the force of gravity. Okay, so I just want to get the acceleration here, so I'm going to take these two things, okay, and I'm going to divide them by m. So I'm going to go, first off, 60 plus negative 49.05, and I'm going to get that F net is 10.95 newtons up. Okay, and then I'm going to divide that by mass. Okay, so acceleration will be F net divided by m, 10.95 divided by 5 kilograms. It'd be like 2.2. 2.2. Okay, that's the acceleration of the bottom bucket. Because it's in a system and connected to the top bucket, it's the acceleration of both buckets. You can. Does that make sense, everybody? Did I do anything different there than I've done on any of the other questions we've done? Sum of all forces, m times a, every single time. Here's what's tricky. Seeing it. Okay, remember how I said you kind of have to see through this? That's true for most Newton's second law problems. You know you're going to get to these two steps. It's how you get there that's tricky. These two steps by themselves are quite straightforward, and they're exactly the same every single time. What's tricky is recognizing that, oh wait, I don't need the top bucket. Because these are in the same system, I only need to calculate one of them.
So how come you didn't lump the two buckets together?
Because I didn't know how much force was pulling on the top bucket. Okay, that's why I said, like, I could assume it's 120, it probably is, but I don't know that for sure. I just want to use the information I know for sure. And in the end, I am lumping them together. I'm saying they both have the same acceleration. Okay? But yeah, I didn't do what I did on the last question, which was combine the masses, because I didn't have information about the whole system. I could only deal with parts of the system and then apply it to the whole system. So first question, we had the whole system, we applied it to the parts. On this one, we had the parts and applied it to the whole.
Would the force applied ever be different on the two different boxes?
If they had different masses, then yes. But because they're exactly the same mass, I would need twice as much force to carry twice as much buckets. Yeah.
So, is that acceleration for just one box, or is that for both?
Both. Right? Like, right? They accelerate at the same rate, right? I almost lost all the masses out of there. I wasn't really thinking when I turned that vertically. Okay. That make sense? Right? So I can apply the acceleration of one part to the whole system and say, because I calculated the acceleration of this one, and they're connected, they can't go faster or slower than each other, so it's the same for the whole system, or it's the same for just this part and that part. You okay with that?
Yeah.
All right, so for question number 2, you have to refer back to what we did here in question in this example here. So I'm just going to pull that so it covers up the other one. Okay, all the things are still the same. Okay, we calculated the acceleration to be 0.36 meters per second squared forward. That piece of information also needs to apply for question number 2. So that's one of your givens for question number 2. Right? So now what they're asking is exactly what I said they might ask. Now they want to know how much force is there here. Okay? How much tension is in this rope? Right? They're telling you that the force of friction on the 10 kilogram block, so on this block, is 14.7 newtons. Okay? We know the total force in the system was 44.1. Okay? 14.7 of that 44.1 is on the first block. Everybody okay with that idea? Okay, so what you need to do, and there are 2 ways to correctly do this, is calculate the tension in this rope right here. Okay, so both boxes are accelerating at 0.36 meters per second squared. This applied force is still 55 newtons. Okay, all that's changed is they told us 14.7 newtons of the friction is acting on the first box. So whatever's left after that is what's acting on the second box. Okay? So there's 2 ways to calculate the tension in the rope connecting the 2 boxes. They will give you the same answer. Right? Here's the tip I will give you. You now have to separate the system. You can solve this with either block. Okay? You need a free body diagram of either block, and you can work it from there. Okay? That force is acting on both blocks in the same way. I'll give you 2 hints. Okay? Here are the 2 hints. They are the free body diagram for each box. The 10 kilogram box is being pulled forwards by 55 newtons worth of force, resisted by 14.7 newtons worth of friction, and what else?
20 kilograms.
Exactly. The force in the rope because of the 20 kilogram box that the 10 kilogram box is dragging. Okay? So there are actually 2 resisting forces. That's the force you're supposed to find. Okay. You could also solve this with the 20 kilogram box. The force acting forwards on the 20 kilogram box is the force we're supposed to find, the tension in the rope connecting the boxes. Okay? There's only one force resisting the 20 kilogram box, and it's the force of friction, and it's 44.1 minus 14.7. Okay? Because we said 44.1 was the total friction on the system. This much was just on the front, so there's 29.4 newtons worth of friction acting on the second box. All right, see how you do from there. Okay, let's look at this one. So, right off the bat, I know the acceleration and the mass of the first block. So what can I calculate with that? Mass and acceleration can get me F net. Okay, so that's what I want to do first. The net force acting on the 10 kilogram block is mass times acceleration. 10 times 0.36 is 36 newtons, and that'll be forward. Positive 36 newtons. All right, so I've now got the net force. Do I know which forces are acting on the 10 kilogram block? So can I do vector sum of all forces here? I should be able to. I better, because that's the other way I have to calculate net force. Okay, so F net is going to be the applied force, that's my 55, plus the force of friction, 14.7, plus the tensional force, which I don't know. But I know 3 out of the 4, so I can calculate the 4th. So if I want to calculate Ft, okay, I'm just going to go F net minus the other one. So minus applied force minus the force of friction. What's key here is the vectors. If I don't assign positives and negatives correctly, I don't get the right answer. Right? So my tensional force is positive 36 minus positive 55, those are both forwards, minus negative 14.7. Okay, friction is backwards. Alright, so I'm going to have 36 minus 55 plus 14.7. Okay. Whoop. Where did I mess up here? That's not right.
Just 10 times.
Hang on. Backwards. 36 is forwards.
Where do you get the 36 from?
The 36 is the net force. Mass times acceleration.
What acceleration is a decimal?
It's 3.6,
Yeah.
not 36.
That's what I
Okay. Yeah, see, that's why you don't do stuff in your head. 'Cause, yeah. 3.6, this will work out much better. I was trying to figure out what I'd done wrong. I was like, yeah, I totally legit did this the right way. Yeah. 3.6, hey, minus 55 plus 14.7 gives me a much better number. That one. Okay. So 37 newtons to two significant figures. But for me, for the 10 kilogram block, this is a negative number. Is that okay? It is. This is the force of the thing behind it pulling back on it. Okay, so it's 36 or 37 newtons, negative 37 newtons. Okay, everybody all right with that? Okay, so that's the first way. That's solving it using the 10 kilogram block. I can also solve it using the 20 kilogram block. So, all right, so I've got my force of friction that I calculated here to be 29.4, and then I've just got the tensional force going forwards. All right, so again, I want to calculate F net, mass times acceleration. This time I'll do it right though. 20 kilograms times 0.36, okay, is going to give me 7.2. I did it in my lesson, I did it in my head again. But I think I did it right this time. 7.2 newtons, okay, and that is positive because this thing's accelerating forwards, okay. Now I'm going to say that F net for this box is the tensional force, which I have to calculate, plus the force of friction, which I already know is 29.4 newtons. So Ft will be F net minus the force of friction, 7.2 newtons minus negative 29.4, still comes out to 37 newtons. It's just from the 20 kilogram box's point of view, that force is forwards. Okay, so I can solve for it using either box. Okay, the importance of this is that this is clearly a system, right? All the forces that are acting in it are shared. Okay, and so it should work out like this. All right, questions on the two block question?
Did it ever ask you to use like a specific, like which one of the blocks to use?
I suppose there's probably situations where it might say using the 20 kilogram block. I wouldn't, because in a situation like this you could use either one.
Okay.
Whichever one you'd be comfortable with would be fine with me.
This is more about the nail one, like when you're lifting it up like vertically. But like if, say the thing, like I don't think we'd ever calculate this, but is there a calculation for like when it's going down and the acceleration exceeds the tension in the rope, and then the top one would accelerate more than the bottom one, or just?
No, that would never happen for this reason. That would mean that if I dropped two objects that were identical, one accelerated faster than the other, right? So the top bucket can never accelerate faster than the bottom bucket, even if I let them go. They're still going to fall together. Yeah? Okay, Pulleys. Are pulleys a system? Yeah, they're two connected objects. All that's changing here is the pulley will change the direction the forces act. Okay? It's a pivot point. It redirects the force, or it becomes, if you put a set of them in there, they become a force multiplier. We're not going to deal with any of those. We're just dealing with single pulley systems. All right, so we got these two objects connected by a light rope over a light frictionless pulley. When they say light, they mean these things have no mass, so that their mass doesn't come in. Because if they don't say that, part of the system becomes the mass of the rope and the mass of the pulley, and I have to include it also. They say light, they mean they don't have any mass and you don't have to include it. Okay? All right, in this situation, so I'm holding this system up so it can't move. If I let it go, what happens? Right. Okay? The 35 kilogram block falls, the 25 kilogram block goes up. Right? What force is acting on both blocks? Gravity. But it's not what? It's not the same. One of the boxes is heavier than the other. Okay? That's why one of them falls and the other goes up. Now, when that pulley system actually starts to move, gravity is the only force in this system. Will the acceleration of the system be 9.81?
Because don't you think we force it?
Exactly. The other box is going to resist the falling of this box. So this box will not be able to fall at 9.81. It wants to, but it can't because it's being resisted by this box, which also wants to fall at 9.81, but is being yanked upwards by the other box. Okay? So, if we're looking at the forces in this system, they are force of gravity and force of gravity. But they're different. Okay. So those are the two forces that are driving this system. And they're working against each other. Okay. So could I simplify this system in a free body diagram? Are these two boxes going to accelerate at the same magnitude? They better. They're connected. Okay? If they don't accelerate at the same magnitude, they're not going to accelerate in the same direction. One's going up, one's going down. But the magnitude of that acceleration has to be the same. Okay? So, I can simplify this diagram. It's a system after all. All systems can be simplified by doing this. Okay, 25 and 35. I got 60 kilograms worth of mass being pulled this way by 343.35 and resisted by 245.25. I mean, that's what's really going on here, right? The net force in this system has got to accelerate 60 kilograms worth of mass. Right? Once I let this system go, that's what's going to happen. 60 kilograms worth of mass is going to accelerate. All right, what can I calculate right now? F net. Yep. I can calculate the net force acting on the entire system. Mass times acceleration, or 343.35 plus negative 245.25, which should give me 98.1 newtons. Okay, what can I calculate now? I can calculate the acceleration of the system, 35 kilogram mass, 25 kilogram mass, of the everything, okay? I was misleading when I said the, okay? I can calculate the acceleration of everything in this system, the system and all the individual parts, because it's all connected, thus it's all the same. Every part has the same acceleration, right? So I'm going to take my 98.1 newtons, okay? Take this, okay, put it over there. So I'm going to have 98.1 newtons divided by the mass of the system. So newtons divided by kilograms will leave me with the acceleration. Okay, 1.6 meters per second squared. Can I put a vector on that if I ask for the acceleration of the system? Nope, I can't, because one part's going up, one part's going down. In a pulley system, you cannot give a direction unless it asks for a specific part, okay? If I was giving this question, I would ask, what's the acceleration of the 25 kilogram mass? Why would I do that?
To trick people.
Yep, absolutely 100% to trick people, okay? Not to be mean, but to check to see if you understand that these have the same acceleration. As soon as I mention one of the masses, people don't put them together. They start treating them like they're separate. Okay? They're together. They're in a system. Okay? All that's going to be different is when I give this acceleration, I now have to say 1.6 meters per second squared up if it's for the 25 kilogram mass, or down if it's for the 35 kilogram mass. But if it says, what's the acceleration of the system, okay, then it can only ask for magnitude. And in fact, the question should actually say that. It should say, determine the magnitude of the acceleration of the system, because there's no way to give a direction in that case. Okay? Because this question said, determine the motion of each object, then I can put directions on. 25 kilogram, 1.6 meters per second squared up. 35, 1.6 meters per second squared down. Okay? All right. Have we done anything weird in any of these? Always been sum of all forces and n times a. I know I've said that like 100 times. I'm going to keep saying it, okay? What's tricky is analyzing the system, okay? Getting it worked out to where it needs to be. All right. Try that one.